Making the invisible visible, a visual guide to EMFs, their effect on people and their environment. As we go through some demonstrations in this presentation, I would like you to keep the following in mind. We're made out of matter. Matter is structured into cells. Cells are made up of molecules, and molecules contain atoms. And what holds atoms together is electromagnetism. So at an atomic level, electromagnetism is essential to life. For the first demo, we're going to look at static electricity. Now, we all know what static electricity is. We've probably shocked a sibling or got shocked by a door handle. And we kind of get this shock and it's uncomfortable. There are actually some health effects that are associated with high levels of positive ions in the environment, which is related to static electricity. Right? So just like this little tinsel orb that we have here, dust particles may stay suspended in an environment with static electricity. And what happens when dust particles stay suspended is we end up breathing in these dust particles. And what can bind to these dust particles are pesticides, VOCs, chemicals in our environment. Oh, I'm back. There we go. Yeah, so this is just a visual representation of what static electricity can do in our environment. These are suspended particles or dust particles will act very similar to this little orb made out of tinsel. Okay, the next thing we're going to look at is just magnetism, as in the magnetic field of the Earth and how compasses work. So the magnetic field of the Earth is a natural form of EMF. And what we have here is a steel rod and a compass. And as I place the steel rod close to the compass, it barely moves the needle of the compass. So this metal is not magnetized. Now, if we take this metal rod and line it up north-south, just like the north-south is on the compass here, and we hit it on the end with a hammer a few times, what happens is we're jiggling around the atoms at an anatomic level, and they will start to slowly align to the magnetic field of the Earth. So when we hold it up to the compass, we now see that the steel is now magnetized. Now, the reason I show you this is a phenomenon happens with metal springs in beds. And just like how I was hitting the steel with a hammer, when the metal springs of a bed compress and decompress at an anatomic level, the atoms may start to align. And sometimes what we do for an evaluation over a sleeping area is move a compass over the bed springs, and sometimes the compass will start spinning because there's an artificial magnetic field based on the springs after compression and decompression. Over time, the atoms might start to line up and create an artificial magnetic field. As a building biologist and electromagnetic radiation specialist, this is something that we may do over the sleeping areas, put a compass over the bed, see if the metal springs have become magnetized. We find that nature's our gold standard. So as close to nature we can get as possible, the greater. And if there's any disturbances to that may have some health consequences. Next, we're going to look at AC electric fields. These are the fields that are found in almost all buildings and built environments. This is what runs your appliances, charges your phone, charges your laptop. And it creates a field that can induce a voltage or electrical pressure on anything conductive. And it just so happens that we're conductive. So it'll induce an electrical pressure or voltage onto us. So these are one of the few fields that we can actually physically see under certain conditions, like a plasma ball, for example. The plasma ball actually shows you these electric fields coming off of the center post of the plasma ball, which is of a high voltage. And when we come up, when anything comes in contact with it, the electric fields just beyond the glass ball find that my hand is conductive and it has an easier time passing through my hand than through the air. Now, the interesting thing about that is this here is a voltage sensor. It's green when there's no voltage sensed. And as I move my hand closer to the plasma ball, it starts to sense a voltage. So it's inducing a voltage on the surface of my skin. And as I move my hand away, it goes away. Now, if we take something conductive and ground it and put it in between myself, if I hold this up very slowly, there we go, right? It says that there's no voltage. So the electric field attaches onto the metal foil and goes through the ground cord to the third prong without inducing a voltage onto myself. Now, if I drop this little foil that's grounded and touch it again, there's a voltage induced. So what happens when we look at a lamp, right? A lamp, for example, has a cord, and this is plugged in. So there's an electrical pressure or voltage induced on the cord up to the on-off switch of the lamp. I'll just move it around there, right? Now, I'm just going to change the setting on my voltage tester to be a little more sensitive. So now it's on a blue setting here. Okay. Again, as I prick my hand closer to the cord, it starts to sense a voltage. Even though the lamp is not on, there's an electrical pressure in this cord that's inducing an electric field. So there's 120 volts in this cord, but it's inducing a voltage on the surface of my skin that's sensed by this outlet tester. So how much voltage? But as I bring my hand closer to the cord, right, we see there are almost 3.5, 3.7, 3.8 volts coupled on the surface of my skin, even though this is turned off, this lamp. But again, there's electrical pressure up to the on-off switch here. So as I'm holding this cord, it's up to 3.3. As I step away, there's about 1.2, 1.3 volts, just based on the lighting and the different things that are currently around me. And if we put that into perspective, you know, that 1.3 volts right now is almost like having a AA battery. A AA battery would be 1.5 volts, but a AA battery is DC electricity. What we're talking about is alternating current electricity. So it's almost like taking a AA battery, connecting it to the surface of my skin, and flipping it from positive to negative 60 times a second. Okay? And that's AC electricity, and from the voltage or the electrical pressure. Okay, now we're going to look at AC electricity and the fields created by when electricity flows. So when I turn on this lamp, there's now a flow of electricity going through the lamp, going up to the light bulb, coming back down, and flowing back through the other wire. So when we have that, the current is flowing in equal and opposite directions, goes up to the light bulb, and returns back. So when it's equal and opposite, there's a cancellation of something called a magnetic field. Okay. Now, if those wires weren't close together to each other, and if we separated them, the cancellation effect wouldn't happen. So here I have an extension cord where I've split the the hot and the return current. So we're just going to turn on a magnetic field meter. And we're reading 0.29 milligauss. We want to be kind of under 1 or less is kind of an ideal target. Now, as we separate these wires, magnetic field increases. And if we zip them together, right, it drops down to almost the background level. So what happens when we're exposed to magnetic fields? Well, magnetic fields will induce a current in anything that's conductive, or anything that's a closed loop, I should say, that's conductive. So if we now turn this off and we go to another source of magnetic fields, which are these wall warts, we'll see a very high magnetic field. Just turn that off because it's going to get a little noisy. So inside of us, we have these closed loops that are conductive, right? The first one that comes to mind is our blood. Our blood circulates through our body in a closed loop. And our blood also happens to be conductive. So what we have here is a closed loop of copper. Okay, and right now there's no current flowing in this piece of copper measured by this clamp meter. So it's reading 0 amps. Okay, and as I hold everything close by, as I bring this high magnetic field point source in contact, we get now 0.2 of an amp. That's 200 milliamps. So we know GFI breakers trip at like 0.005 of an amp or 5 milliamps. And this is 210 milliamps, just induced by the magnetic field from this transformer, right, on the copper line. So now what happens when we actually open up this loop? Right? So as we open up the loop, if I point this in the right direction, right, we see no current flow. If I close the loop, I have to tighten this up to make a good connection. Right, it goes up to 0.2 of an amp or 200 milliamps. So that's just a demonstration how magnetic fields may interact with the human body. So now we're going to talk about dirty electricity. And this is simply just electrical noise on your electrical system. And our electrical system typically works at 60 hertz. And the noise that rides on the electrical system can be higher than that. Just like as you're driving and you're listening to an AM radio during a thunderstorm, you'll hear these cracks and crackles, and it creates noise, so you can't actually hear the music or the radio station, the AM radio station that you're listening to. So this electrical noise can create noisy body voltage. It can create noisy currents inside of us in our closed loop of our blood and our circulatory system and other systems in our body. And let's just take a look at what this looks like. So here I have two sources here, and I'm going to just start off with simply using an AM radio. So right now the AM radio is just tuned to a station that doesn't have any radio station on it. Okay, and what I'm going to do is I'm going to turn on a couple of devices here that I know have that are creating some electrical noise or dirty electricity. So first is the compact fluorescent. Now, as we move the AM radio closer to the light, you can actually hear the noise. And this noise is coming off of the wires, and it's actually coming off the bulb as well. You can see if as I put my hand in front of it, the noise gets less, right? I'll put it up really close. Right? It's a little louder when I have my hand away. So now we're going to turn this device off, and now we're going to look at this lamp. Okay. This lamp is particularly noisy. It's running off of a DC light, so that's to convert the AC electricity to DC electricity, which the light bulb needs. And that conversion process in this particular lamp is pretty dirty. That's a lot of electrical noise. So we can look at it in a different way as well, using an oscilloscope. So on the oscilloscope, you're going to see this red trace. And basically, we have it hooked up to an antenna here. And the antenna is going to pick up the radiated electrical noise in the environment. So right now, it's just kind of a flat line. When I turn on the compact fluorescent, you start to see a little bit of noise. And as I bring it closer, you start to see the noise increase. Okay. As I move it away, if I put the AM radio over here, right? So the dirty electricity is actually passing through the air. Now if I turn this off and turn this one on, this one's quite strong. You can see right away. Right? It gets quite strong as I move it closer. Now if we contrast that to what happens with an incandescent light bulb, we see no change in the AM radio sound. And we see no change in the oscilloscope. Okay. Now there's even another way we can look at this, and that's through current. So what we know is as the frequency increases, basically a higher pitch electrical noise, our body resistance gets lower. So basically, at a certain point, the dirty electricity is at a certain frequency, it's going to start passing through our body versus just riding on the outside of our body. So as frequency increases, our body resistance decreases. So right now, I'm measuring my body current. So this is in reference to ground. And I'm in quite a noisy environment right now. So I'm reading about 18 microamps. And that's considered a carcinogenic level from a NOSHA study, a .gov study in the US. And they basically state that once you're above 18 microamps, the electric field that gets generated from that inside your body is at a carcinogenic level. So when we're in an environment where we increase the dirty electricity, for example, turning on this source, and let me just put on the frequency here so you can see it. And I have about, about 17 microamps or 18 microamps. So I'm just going to turn on the lamp. And as soon as I do that, I'm just going to turn off the AM radio here because we know that it's, right? We see the oscilloscope go up. We see that we're now at 25 kilohertz, 25,000 hertz. Instead of 60 hertz, which runs in our electrical system, we're now at a much higher frequency. So there's quite a bit of electrical noise at 25 kilohertz. So when that frequency increases, there's more current that can pass through me, measuring myself using a body current method. And if I turn that off and just go to the incandescent light, you notice there's no real difference here. I think I'm at 19. Now it's about 18, 19. And when I hold my hand up to there, even grab onto the, oh, start to see a little bit of frequencies when I grab onto the actual lamp itself. As I come away, it's at 19. So we do have some dirty electricity. We have some LED lights on for the lighting and a few other devices that are plugged in. We have a few laptops that are recording the video and all that. So this is not the cleanest environment. Usually the number is below 8 microamps. So that's just a few different ways that we can look at this dirty electricity and how it kind of interacts with the body. So let's talk about wireless technology. This includes Wi-Fi, Bluetooth, baby monitors, cell phones, smart devices like speakers and thermostats. They're really everywhere now. And the way that wireless technology works is there's a transmitter and a receiver in each device. And that's how they communicate to each other, is they send a transmission and then they receive a signal. And an analogy that we like to use is with sound. So sound has frequencies as well. There's high-pitched sounds that are at higher frequencies and lower-pitched sounds that are at lower frequencies. So I'm just going to play a video of how tuning forks transfer energy. And it's going to talk about resonance, which just means if two tuning forks are tuned to the same frequency, that means they have the maximum energy transfer between those two. So I'm just going to play that now.
Demonstrations is that of resonance. I have these two tuning forks which are on the same frequency, 256. If I sound one of them, the sound gets transported to the other through resonance and back again. Here's a way you can enhance the demonstration. I've hung a ping pong ball on a string and it's up against the edge of one of the tuning forks. Watch what happens.
This concept of resonant frequency is important, basically because people are conductive and they're going to have a resonant frequency, right? Me standing here, I'm about 6 feet tall, so I'm going to have a resonant frequency of about 100 megahertz, which is kind of around the frequency of FM radio stations. Now, if I put my arm out, if I put this arm out, right, it's going to have a resonant frequency of something different, right, because it has a different length to it. And there's also been some studies about how our DNA is actually called has many properties of a fractal antenna, which just means it can sense a large variety of frequencies, or a wide bandwidth of frequencies. So it's just interesting how resonant frequencies can actually resonate with our body. And it's often been wondered if people with implants, maybe heavy metals in their body, they might resonate better at certain frequencies or absorb more of the energy, have more energy transferred to them. So it's just an important concept to understand, is this transmission of energy is basically like electricity through the air. And when we think about all the devices and all the transmissions that are happening, there is quite a bit of energy when you sum them all up, right? Whether it be from the cell towers, whether it be from AM, FM radio, TV broadcasts, there's the airport radars, there's planes. They're now building in different safety systems into vehicles for adaptive cruise control, lane change assists and things like that. And they're using wireless frequency, or basically frequencies, radio frequencies, to sense these to make these decisions and to sense what's going on around them. So it's just an interesting concept that I don't think gets explored very often, that I just wanted to bring to light. And if you want to hear the sounds of a microwave oven and a cordless phone and a Wi-Fi router, go check out Rob Metzinger's webinar on the EMF medical conference website. To just demonstrate how this is actually transmitting almost electrical energy between the two of them, what I have here is a passive device, and it's almost like an energy harvester that takes the energy emitted from the Wi-Fi and translates it into a little light. So what I'm going to do is just set this up. If I can balance it there. Then I'm going to hit the button and you'll see these two lights come on. If I do this right, I'm just going to turn the Safe and Sound Pro so you can hear the sound. So I have a few things going on in the background. But I'm just going to hit the button here and you'll start to hear a helicopter sound. There we go. Okay, that is sending out 10 duts per second, and that's the network ID. So this broadcasts 24/7. It's a digitized signal. It sends this out as pulses, whether you're using the internet or not. As long as the Wi-Fi is on your device, it's going to be sending out these transmissions. Now, if I kill the power, what I want you to do is look right here. And what you should see is a red light flashing kind of at the same rate as the Safe and Sound Pro, right? So that light is flashing at 10 times per second because it's actually harvesting the energy from that antenna. Basically, the Wi-Fi router is sending this information wirelessly. It's almost like sending electricity through the air. Now, if I turn off the Wi-Fi, so you'll see these two lights turn off here, and the sound goes off, the blinking stops on the energy harvester. I'll just turn it back on. Right. And the light starts blinking again on the energy harvester. So that's just how electricity is passing through the air. So the next thing we're going to look at is light. And obviously light is a visual thing, but there's many ways that we can measure the quality of light. And we can look at the flicker rate, we can look at the amount of blue light that comes off of a light. We can look at there's a bunch of different parameters, like flicker index, percent flicker, how much maybe magnetic field or EMFs come off of it. Lights can produce dirty electricity, they can create electric fields, they can create magnetic fields. There's many components to lights. So I was just going to focus in on one component of it, and that was flicker. And the reason why I want to focus on it is because it's one that's kind of, most people with a smartphone can get an idea of what the flicker might be off of a light. And basically what you do with your smartphone is you do a super slow motion, not a slow motion, but a super slow motion video capture of the light. And you'll be able to see flicker from monitors, from computer screens, tablets perhaps, from different lighting, even Christmas lights and things like that. So it's a very accessible tool to use. Even an incandescent light will have a flicker effect to it where it dims slightly and gets brighter. But some LEDs will actually physically turn off and then turn on. You'll actually see a shadow cast when you slow everything down with a super slow motion video. So I'm just going to show you a couple of videos here just to give you an example of what this might look like. So you can definitely see in this video when it's slowed down, you can see the flicker rate on the one monitor with the landscape in the background and no flicker on the other. And there is no real standard or quality assurance when it comes to flicker. There's a few brands out there that advertise no flicker, or they have like an eye care or something similar type of monitor, and those typically tend to be the better ones. So that's it. All video footage is from a TV, and you can see the flicker rate and the refresh rate of it is very sporadic. And this is happening all the time while you're watching the TV, even though it's not perceived when you look at it. But these flashing and things are actually coming at you. So this can cause like eye strain, headaches, and migraines. And there's probably more that we don't know about the actual effect of this. Again, this is some track lighting with some LED light bulbs. Again, you can see the flicker rate. Here's an LED light. So this is one that doesn't have a light bulb in it. It's just a ring of LED lights. There's nothing to replace in it. Here's a hardware store with lots of lights options, and you can see they all have kind of different flickering at different times. This is a super slow motion video of it. So some have none, some have significant, right? You see some actually physically turn off. That concludes the visual demonstrations for the presentation. I just had a couple of quick slides about the Building Biology Institute, the sponsor of this presentation, and specifically about how to get EMF help if you're looking for it. Where to find EMF help? So if you're looking for a hand in exploring your electromagnetic field environment in your home and looking for mitigation strategies, I highly encourage you to go to the buildingbiologyinstitute.org, click the Find an Expert link, click the Certified Consultants, and click the Electromagnetic Radiation Specialists. There's going to be a list of over 40 people that can help you out and help you steer you in the right direction. I know during these times, a lot of the people on that list are doing telephone consults or video consults as well, just to be a little more accessible to people. So just a little bit about the EMRS, or the Electromagnetic Radiation Specialist Program at the Building Biology Institute. Everyone who becomes certified goes through this process. There's a self-study course on natural, healthy building, and it takes about 2 to 3 months to complete. It's quite comprehensive, and it goes through kind of a holistic view of the building biology principles. So this includes indoor air quality, water quality, a little bit about electromagnetics. You get a radon test puck, so you get to test the radon in your home. You get a little magnetic field Gauss meter to test some magnetic fields in your home. There's a mentor that's set up for this self-study course. And like I said, it goes through kind of the basics of building biology and the principles, and has you apply these principles to your own home. There's also 12 online exams. Some of them are on 5G, some of them are on cell phone technology, electrical wiring, lighting, so on and so forth. Then there's 3 5-day seminars. One's on building physics and building biology, and the other 2 are on electromagnetic radiation. So out of the 80 hours just spent on the 2 5-day seminars, about 50% of them is lecture and 50% of them is hands-on. So during these in-person sessions, you get to actually get your hands on meters, and you spend about 40 hours in total in labs, actually taking measurements and going through test procedures and protocols, just to help solidify some of the theory that has been taught in the lectures. And finally, there's a mentored final project where, under the wings of a certified EMRS, the student goes in and does their own assessment and comes up with their own report and findings. So it is quite comprehensive, probably one of the most comprehensive programs out there. And I just wanted to make note that the building biology has other certifications. They have a building biology advocate. They have a building biology environmental consultant, which was the flagship program. They deal with, indoor air quality, emissions, airborne toxins, mitigating, eliminating pollutants. So that used to be the main program that we had. And then there's also a building biology new build consultant. Those are for people who are looking at new builds and looking at building materials that are healthy and natural, and how to reduce those as much as possible, along with some electromagnetic radiation design. So if you're interested in those, please head over to the Building Biology website to check those. Electromagnetism is essential for life, as I started off. It's also essential for technology. And when those two merge, it's just an interesting intersection of navigating that. So if you need any help, please reach out to the Building Biology Institute, the EMRS specialists, or an EMF consultant near you.